You ever just stop and think about this incredible paradox? Everything that's alive, you, me, that tree outside your window, all of it, is built from stuff that is completely not alive. Lifeless atoms and molecules. So how in the world does a pile of non-living chemicals get together and create something as complex, as amazing as life itself? All right, let's get into it.
This quote just hits the nail on the head, doesn't it? Life isn't really a thing. It's a process. It's this beautiful, perfectly timed chemical ballet. And today, we're going to pull back the curtain and meet the dancers in this ballet, the biomolecules. And here they are, the stars of the show, biomolecules. These are the bridge between simple, boring chemistry and the absolute wonder of biology. On their own, they're just lifeless chemicals. But when they get together and start interacting, well, that's when they create the logic of life itself.
Okay, so here's our game plan for this explainer. We're going to start with the body's main fuel source. Then we'll meet its tireless workers. After that, we'll uncover the master blueprint for the whole operation before we tie it all together at the end. All right, let's kick things off with our first group, carbohydrates. You know them as carbs. These molecules, which are mostly made by plants, are basically the energy currency for pretty much all living things. Think of them as the high-octane fuel that powers everything, from you running a marathon to just the neurons firing in your brain right now. So how are they put together? Well, it all starts with these tiny, simple units called monosaccharides. You link just a few of those together, say 2 to 10, you get an oligosaccharide. But when you link thousands of them in a massive chain, now you've got a polysaccharide. It's kind of like going from a single Lego brick to a small little build to a giant castle.
And you want to know a really simple way to tell them apart? Your tongue. Those smaller units, the monosaccharides and oligosaccharides, yeah, those are what we call sugars, and they taste sweet. But once you build those gigantic polysaccharide chains, like the starch you find in a potato, the sweetness just vanishes. They become non-sugars.
You know, this simple drawing actually hides a fascinating little detective story about glucose, the most common organic compound on Earth. For ages, scientists were puzzled because its simple chain structure just didn't explain how it acted in experiments. The answer? It turns out the chain cleverly curls back on itself to form this super stable ring. It's an elegant solution that solved the whole mystery.
So the big takeaway here is that carbs are incredibly versatile. They can be a super quick hit of energy, like the glucose you get in honey. Or they can be packed away for later, like starch in plants or what's called glycogen in our muscles. And get this, they can even be used as a building material, like the super tough cellulose that gives plants their structure.
Okay, so if carbs are the fuel, what's the fuel actually powering? Well, that brings us to proteins, the body's workforce. Seriously, these are the most abundant biomolecules in living things. They are the builders, the machines, the messengers, they do pretty much everything.
So how are these amazing workers built? They're made from 20 different kinds of building blocks called amino acids. But here's where the magic really happens. A protein's job isn't just about which amino acids it has. It's about the exact sequence they're linked up in. You change just one amino acid in that long chain, and you can completely change what the protein does.
And this image shows you exactly how that sequence creates a functioning machine. A protein starts out as just a simple chain of amino acids. That's called its primary structure. But it doesn't stay a floppy chain. It immediately starts twisting into coils and folding into sheets. That's the secondary structure. Then, the whole thing folds up into a unique, complex 3D shape, its tertiary structure. And for some proteins, a few of those blobs team up to form the final machine, the quaternary structure. It's that final 3D shape that lets it do its job.
Now, because that intricate 3D shape is so absolutely critical, it's also pretty fragile. If you crank up the heat or change the pH too much, the delicate bonds holding that shape together just break. The protein unfolds, we call that denaturation, and it completely loses its ability to work. The classic example? When you boil an egg. The clear protein in the egg white denatures and turns into that solid white mass, and there is no going back from that.
Okay, so we've got our fuel and we've got our workers. But what tells the workers what to do? What tells them what to build? For that, you need the master blueprint, and that brings us to nucleic acids. These molecules are the information archive of life itself.
And here it is, probably the most famous molecule in all of biology, the DNA double helix. First figured out by Watson and Crick, this elegant twisted ladder is just a masterpiece of natural engineering. The two strands fit together perfectly, which is crucial because it protects the precious genetic code, the sequence of chemical letters, that's tucked away safely on the inside.
Now, DNA isn't the only nucleic acid on the block. It's got a very important partner, RNA. They're super similar, but they have a few key differences. They use a slightly different kind of sugar in their backbone. RNA swaps out one of the chemical bases, thymine, for a different one called uracil. And maybe most importantly, DNA is that stable, two-stranded helix, while RNA is usually a more flexible single strand.
So, why the differences? Well, it all comes down to their jobs. The best way to think about it is this. DNA is like the master blueprint, locked away in a safe in the main office. It holds all the permanent genetic information, and you don't want it getting damaged. RNA, on the other hand, is like a temporary photocopy of just one page of that blueprint. It's the copy you take out to the construction site to actually tell the workers, the proteins, what to build.
So, there you have it. We've met all the main players. Let's bring them all back out on stage and see how this amazing chemical ballet comes together to create what we call the molecular logic of life.
So let's just do a quick recap, a final roll call. You've got your carbohydrates, providing fuel and building materials. You've got your proteins, the versatile workforce that does, well, everything. And you've got your nucleic acids, the master blueprint that holds and transfers all the instructions. Each one has a totally essential job to do.
But here's the most profound, the most incredible truth of all. None of them work alone. Life isn't in any single molecule. Life emerges from the countless, complex, coordinated interactions between them. It's the constant, harmonious dance of these lifeless molecules that creates the vibrant, incredible process that we call being alive.
And that brings us right back to where we started. We are made of the exact same non-living chemical stuff as distant stars and common rocks. It's just organized in a way that allows us to think and feel and wonder about it all. So I'll just leave you with this to chew on. These non-living molecules create everything we call life. What does that tell us about our place in the universe?